Hello everybody and welcome to another online seminar presented by Head Acoustics. My name is Jacob Sondergaard and I will be your host today. Today's topic, we will be focusing on something called listening effort, and specifically on how we could possibly optimize the listening effort of certain communication devices. The agenda that we would like to go through today involves a little bit about background and motivation for putting this together and discussing listening effort. We'll talk about some recent trends in the standardization community, where we'll touch on a MOS metric specifically for listening effort. We will then dance right into the head acoustics environment and talk about the implementation there, something we called ABLE, A-B-L-E, Assessment of Binaural Listening Effort. Then we will share some fantastic practical applications, use cases, and of course, real life results from real off-the-shelf devices. At that point, we'll wrap things up, put a nice big bow on it, and we'll send you on your way. Now, to start off with, why are we even doing this? I think to frame the conversation, it's no secret that as we move around and we use our devices, we also get into situations where we run into high noise environments. However, in tune with maybe the increasing daily noise environments, we also increase our expectation for that device performance. We are creatures that enjoy the ability to communicate, and we have very high expectations for the types of products that you may be making. And the pressure that has been put on the industry to evolve and improve devices has grown exponentially. What we're seeing is a lot of these mobile communication devices feature a lot of speech enhancements on the receive side. And a very typical example of that is what we call ANC, or active noise cancellation. This is not just something that's unique to ANC headsets, but also something that's trickled into mobile phones. And there's a lot of other technologies on that receive side that is supposed to improve the quality of that received speech despite the ambient noise conditions. Now, of course, the noise conditions that we run into today don't just include highway noise like shown on the picture here. Very often we're in a crowded environment. There's lots of other people around. There's what we call maybe babble noise as the background. Speech is part of that background noise. And of course, our device is trying to optimize the speech output. So things can get a little tricky and a little hairy. Nonetheless, we, of course, have some perceptual-based methods for evaluating speech quality and, to an extent, intelligibility. However, the key thing that we want to drill into today is none of these methods were really available for either the speech intelligibility and or listening effort on the receive side of a telecommunication system. Now, when we talk about some of the enhancements that are being applied, it all sort of falls under the umbrella of near-end listening enhancement, NELE, NELE, as we might call it. And some of those technologies, like I touched on earlier, include active noise cancellation, but it's also simple things like AGC or volume control, and it also includes things like artificial bandwidth extension. So if you're in a narrowband call, the phone or the communication device might try to get sophisticated and improve the bandwidth to improve the quality of the speech, but maybe also to improve the intelligibility under certain circumstances. And in the automotive domain, we also have technologies like in-car communication, where specifically in three-row vehicles, it allows the driver to more easily communicate with the third-row passengers without having to turn their head around and basically remove their eyes, ears, and focus from the road ahead. Now, just a quick note, all the automotive related applications and technologies, we're going to discuss that in part 2 of this session coming up next month, and will eventually also be hosted on our YouTube channel. Anyway, the whole point and the reason for doing this is it's basically been nearly impossible to predict the performance of any of these processes on a signal being evaluated in the near end or the receive side of the terminal. Now, why are we talking about listening effort? So, without going into too much detail here, there are a lot of existing metrics out there that to some extent attempt to address the issue of intelligibility and quality of the speech. However, all of them have some form of limitation. Some of them, of these metrics, they require that we separate the clean speech from the noise component. Some of them require that the noise is stationary only and don't really work with the dynamic nature of the environment that we are in. Some of them don't really apply and are designed for non-linear process signals, which that's pretty much the essence of a voice signal being transmitted today. And of course, some of the metrics that we know, they don't work or function either in the presence of noise, full stop, period, or they aren't really suitable or designed for the near end or the receive side application. So bottom line is we do have a online seminar that addressed some of these simpler intelligibility metrics on our YouTube channel. I would encourage you to go and explore that if you're interested in more details here. But for now, the point is nothing really fits the application that we're trying to address. And one of the very typical applications that we'll touch on here today is, for instance, using a pair of ANC headphones in talk-through mode. So the idea is that ANC headsets now have multiple modes. One of them is this talk-through, hear-through, pass-through mode. It's called a bunch of different things. Whatever the name, the goal is always to try to allow speech in the near end to pass through the headphones without having it be degraded, while having it be intelligible, and without having too much background noise feeding through the system as well. So it's a bit of a challenge, and this is a technology where we really need to figure out how can we best possibly analyze that situation. Now, if you revert back to subjective testing and auditory testing, of course we go back to the old challenge of the fact that however you end up doing this, it's always going to be a time-consuming affair that is fairly resource intensive and potentially error prone, because frankly you're dealing with people and people can be unreliable. And one of the things that we want to take into account here when we look at listening effort going forward is we want to follow the latest trends in standardization, which means we want to use real speech. You know, that's one of the limitations with some of the older metrics is they're not really adapted for real speech. They require some form of simple, pure tone or simulated speech. We want to use real speech. We also want to use real and realistic background noises, not just a pink noise scenario. That's not going to cover it. That's not going to put our device into a realistic state that the user might find themselves in. And then finally, we want to be able to do this from a black box approach, meaning we want to take devices that are commercially available off the shelf and then perform the testing and do the evaluation that can give us some meaningful results. We don't want to force and require people to hack into the device, tap into signals electrically or wirelessly or other means that aren't made available by the device itself. Now, of course, some of the challenges with the measurement technology include the fact that the device doesn't always behave in a purely deterministic and noise-dependent fashion. Another one is that the level increases that we may see from something like an automatic gain control may end up violating some loudness rating requirements. And the other thing is, as a designer, if you're so intent on tuning towards speech intelligibility, you may also end up inadvertently decreasing the speech quality. So these are all things that we have to take into account as a designer and certainly also as a tester. Now, For certain noise scenarios, though, I think it is worth pointing out that speech intelligibility may actually be more critical than speech quality. And I've listed a few different examples here. I think some of the ones I really want to highlight here, for instance, is an emergency call feature, maybe closely tied in with mission critical voice. So that's the first responder community, where they're not necessarily interested in how beautiful the message is, as long as they can understand what the message is, what the point is, and what they need to do and what they need to act on. And sort of related to that, public service announcements, very typical example is the airport lounge scenario where you're sitting around waiting for your flight. Remember those days? And you're waiting for the announcement, but you want to be able to understand what gate you're going to and what time and if there's any delays. So listening effort, there's some overlap in relationship to speech quality, but it's not quite the full evaluation. It lives a lot closer to the intelligibility domain. And not to spend too much time on this, because as this isn't really the format or the venue to share a lot of the math and the science behind this, but suffice it to say that there were a lot of things that went into the design and development and standardization of the listening effort metric. The thing that I want to point out is that there is an application note upcoming where we would like to contact you and share that information. So please reach out to us, let us know if you would like a copy of that application note when it is available, and we can go into a lot of the hairy details behind it. Now, quick look at the standard. So the Etsy community got together in November of 2019 to standardize what they call assessment of listening effort under the name TS103558. The standard crucially includes both procedures and the rigmarole for conducting an auditory assessment specifically for this type of situation, listening effort on the receive side, as well as the information regarding the instrumental or the objective assessment of listening effort. So the standard includes both. And very, very recently, August 2020, the standard was updated, now includes multiple languages, a lot more use cases. And just so we're all clear, we're still using the MOS scale according to ITU-TP 800. And you can see we've listed the listening effort score. Again, we go from 5 being the highest, 1 being the lowest, and then alongside it, we've listed the equivalent speech quality descriptors. So when we talk about listening effort scores or MOS scores being a 4 or a 5, obviously that's good or excellent. But specifically for listening effort, it means that really there's no effort required. You can be completely relaxed when you're listening to this message. You have complete understanding of what's being transmitted. On the other side, a MOS score of 1 means the speech quality would be bad if we were doing a speech quality evaluation. From a listening effort perspective, it means a 1.0, no meaning whatsoever can be understood regardless of how much effort you are applying. Now, let's look at the general measurement setup for what we're trying to do here. So with all things head acoustics, we're using our primary signal analysis, signal generation tool, Aqua. We use that to control our LabCore interface, which controls the signals going to and from the head and torso, as well as the device under test. In this case, we have a Bluetooth headset mounted on the head and torso in a sound field. That sound field, of course, is run by our 3-pass software. The key thing is it is compliant with Etsy TS103224. It uses the 8 mic and 8 speaker configuration. And specifically for this though, we're using the openness of the MPNS, multi-point noise simulation description in the Etsy standard to allow for an 8 microphone array that is symmetrically equalized around the left ear and the right ear. So what that does is when we're doing our background noise recording and then later the equalization in our chamber, we end up with a sweet spot around the left ear and a sweet spot around the right ear. that's where we are interested in measuring our signals at the ears of the head and torso. Now, the other thing is for the measurement setup will also include a mobile phone. And in this case, our mobile phone will be both in a handheld hands-free as well as in a handset mode. But generally, the setup is exactly the same. And the key thing is for both applications, we will be capturing the binaural recordings. So left ear and right ear. And as you might imagine for smartphone applications, we typically only hold the phone up to one ear at a time. So, as you might also imagine, the listening effort is hugely affected by how much noise that's at the open ear, typically the left ear. Now, let's look at the first measurement challenge. So, specifically what we would like to do is we would like to place a pair of ANC headphones onto a head and torso, put it in the sound field, and then we want the speech to originate from the headphones themselves. This could be either generated locally, like listening to a podcast, or it could be we put the headphones into a simulated phone call, so we're getting some downlink speech. The point is the speech is originating from inside the headphones, it's firing right into the ears of the head and torso, and then we capture that binaural signal from the left and the right ears with all the ambient noise around it. And of course, we have some expectations on what the best listening effort situation would be. For this case, we would assume that the max ANC on those headphones is going to give us the best listening effort results. So this is a situation where talk-through mode is probably not the best because we don't want to concern ourselves with the outside environment. Now, of course, similar to that is the mobile phone case. We're simulating a phone call. Speech is being injected into one ear of the head and torso, as well as there's the ambient noise around. The left ear is only getting the ambient noise. There's no speech signal, and we want to evaluate what is the listening effort in that situation. Now, measurement challenge 2, this one is going to be unique to ANC headsets, but this is one thing that we can start to evaluate with listening effort that previously was fairly difficult to do, if not impossible. The idea is that we want to simulate a second near-end talker. So now we want to put our headphones on the head and torso, the primary head and torso where we're capturing the binaural signals. We have ambient noise playback, but we have the speech signal originating from the secondary talker. That is fairly directional speech pointed straight at our user or our primary head and torso. The use case that we're simulating here, of course, is let's say you're sitting in a noisy environment. You could be at a pub or a cafe, you could be on a train, and somebody approaches you and they want to ask you a couple questions. The goal, of course, with the headsets now is a lot of them have this talk-through mode. And we want the talk-through mode to perform so well that you don't have to remove the headset. Because one of the things that we can do here is we can benchmark the talk-through mode against all the other modes of ANC on the headphones, but also we can benchmark the talk-through mode against the no headset scenario. So simply remove your headset, we still have ambient noise in the near-end talker. Where do we get the best listening effort? Now, the goal from a ANC headset designer perspective is we want the talk-through mode to exceed the listening effort of the no headset situation, because otherwise your users are pretty quickly going to figure out, I'm just going to have to remove my headsets. That's not what we want to achieve. Now, the third measurement challenge is going to be very similar to the second one. The only real difference here is we're replacing the secondary talker with a loudspeaker. And we're simulating now this public service announcement, public address system, where the speech is going to be a lot more diffuse. But otherwise, our expectations are the same for the headset. That talk-through mode is going to allow us to pick up the public address system speech as best as possible while still allowing us some isolation from the ambient background noise. That's our hope and that's our expectation. Now, what we typically do is, or what we typically see people do, is they will put the headphones, ANC headphones, on a head and torso, maybe expose them to some pink noise, and then we will measure the noise plus speech at the left and the right ear for each of the headsets. And then that's what's shown on the left-hand side for ANC headset A and B. A is shown in black and B is shown in green. This is just for one channel, of course. And then on, just for fun, people will always also do the noise-only recording. So there's no speech playback. This is probably just ANC set to max. And we can start to make some assessment of how the ANC performs. If we just for half a second focus on the right-hand side, because it's really not the topic of today, but on the right-hand side, it's fairly straightforward, fairly established that if we're just doing a max ANC evaluation, we can compare not only the time domain plots, we can see there's a difference. ANC headset B appears to perform much better than ANC headset A. We can quickly do a spectrum analysis and compare the two spectra of the headsets to see who achieves the most attenuation in which frequency portion of the spectrum. And then if we get really sophisticated, we can start to do things like apply psychoacoustic metrics, Wicker loudness, speech intelligibility, and evaluate the psychoacoustic performance and really the ANC performance on a scale of subjective magnitude. That's super fascinating and somewhat well documented, but it's not really the topic of today. The topic of today is the left-hand side, because when you look at the left-hand side, we have that mix of speech and noise, and it's impossible for us to go down that path and figure out which headset performs the best using those traditional metrics. So we have to turn to a different analysis method. So if we look at the spectrum, you can see that this is the speech plus noise measured at the ear of the head and torso with the ANC on. We don't know what is what here. Of course, we can see headset A and headset B differ, but we don't really know if it's meaningful. We can make some guesses if we start to look at maybe the raw response of the noise with no headset on, and maybe just the speech playback with no noise. But all we're doing here is making guesses, right? The big question and the rhetorical question that I'll pose today is, how do we judge that performance just based on this graph and the time domain plot on the previous slide? It's nearly impossible. So what the listening effort metric allows us to do is not only plot the listening effort on an absolute scale, but it simply allows us to evaluate this in a way that we couldn't do before. And so when we start to look at these results for our ANC headsets, we can first of all do multiple noise scenarios. We've chosen 4 different noise scenarios here. And we can start to look at the objective magnitude of the listening effort, as well as how they compare between A and B, and we can start to benchmark the headsets. Now, specifically, if we're interested in these 2 headsets, we can see that, maybe no surprise, headset B does perform better than headset A. However, the delta does change depending on the background noise scenario. So for instance, the train noise though, headset B is significantly better than headset A, whereas with road noise, the difference is not as severe. But these are the types of evaluation that are now possible for us to do. And if we were to look at the headset speech playback, if we switch from a narrowband mode, which is the data shown at the top, and then also apply the same speech playback in super wideband mode, we can also see the difference that the device performance gives us. And we can see things like, in general, increasing the bandwidth of the speech playback in noisy environments tend to give us a greater listening effort, at least for ANC headsets. And I think that makes sense when you think about it, because we're isolated from the background noise as much as possible. We're just interested in creating as much content as possible and expanding the content by improving the bandwidth, moving from a 4K limit to a 16K limit, narrowband to super wideband, gives us more of the desired content while the ANC is cranking and trying its best to reduce the outside noise. Now, what about mobile phones? Because as we touched on earlier, these mobile phones are getting very sophisticated. There's a lot of processes taking place. And when we do a quick measurement, in this case, we've taken 2 measurements here from the cafeteria noise background noise example. What we're measuring on the left-hand side is the noise at the ear of the head and torso, the cafeteria noise shown in red, and then narrowband speech from a mobile phone shown in black, and super wideband speech out of that same mobile phone shown in green. On the right-hand side, we have the same scenario, except this is now hands-free. So we have the cafeteria noise and the narrowband and super wideband speech. But the questions that we want to ask is, how does the background noise level and the temporal components affect the device state? Will the device end up, applying ANC, or can the user enable ANC in that mobile phone? Or what about AGC? And are those technologies even effective? Does they actually improve the listening effort? And what about the user volume control? Because the user has the ability to switch the volume up and down. But do we then run into situations where the user volume control and the AGC from the device start to tap into the limits of the audio playback system? And what about bandwidth? How does that affect intelligibility? And if the device is sophisticated enough to have things like bandwidth extension technologies, if you're in a narrowband call and you apply the bandwidth extension, is that as effective as simply having a super wideband transmission? These are all fantastic questions, but how in the world do we extract the answers from spectra like the ones that we're showing here? That is nearly impossible unless we use something like the listening effort metric to give us some insight. So for the mobile phone case, let's focus on the handset mode first. The first thing we want to do is let's look at the bandwidth comparison. That's shown in the top right-hand corner. Now, I think maybe no surprise, our expectation here actually for both bandwidth and volume is probably that if you have a wider bandwidth and if you have higher amplitude speech, chances are you're going to get higher listening effort scores, i.e. a lower amount of listening effort. Now, if we look across the bandwidth comparison in the top right, you can see that's basically true. As we go from a narrowband situation to a super wideband situation, our MOS scores go up. And of course, from the objective standpoint, you can also start to compare and see, well, the noises that are very dynamic, like pub noise, lots of transients, lots of babble noise, we have much higher listening effort and therefore a lower MOS score. And the noises that are not as dynamic, so for instance, car, driving noise, or obviously silence, clearly we have a lower amount of listening effort and therefore a much higher MOS score. So I don't think there's any surprises in that. Now, when we look at the volume comparison, so now we move to the bottom side, we can see that, first of all, measuring the RLR, so in quiet conditions, we measured the RLR of this device, and we can see that clearly we're getting a big SNR boost when we move from nominal to max. That SNR boost is, in theory, supposed to help us. And we can see that when we look at the scores, generally that is the case, especially things like car noise and cafeteria noise. Now, for the silence condition, bumping from nominal to max volume doesn't actually help us. And for crossroad, it actually made it slightly worse. Now, some theories behind this, of course, is that when we increase the volume to max, what we also do is we put a lot of stress on that sound playback chain. So not only the loudspeaker, but the amplifier. And we might be pushing that system to the physical and or electrical limits. And what that means is we could end up, despite the increased SNR, we could end up introducing a lot of distortion, which in turn will reduce the playback quality, but also increase the listening effort and therefore give us a slightly lower MOS score. So if nothing else, this shows us that our expectations aren't 100% met for the handset mode when it comes to bandwidth and volume comparisons, and just emphasizes the need that we really need to do this testing and validation before we release the product. Now let's look at the hands-free mode. So for hands-free though, things go really pear-shaped. All our expectations that we had for handset mode, which were mostly met, are almost entirely opposite for hands-free mode. So obviously looking at it objectively, first thing we notice, silence conditions, fairly good listening effort MOS scores, and they're a lot lower for noisy conditions. No surprise there. Now, looking at the scores where we compare the bandwidth, narrowband, and super wideband, we see that almost all situations result in a lower MOS score when we move to super wideband. Why is that? So a couple things that we point out is that the RLR of the device, measured in quiet conditions, is going to be higher when you're in narrowband mode versus super wideband. So right off the bat, when you move from narrowband to super wideband, you actually lose probably some SNR because the device output is going to be lower. Why? Well, the device is now focused on not just producing audio content in sort of the 300 hertz to 4K range. Now it has to produce content in a much broader frequency range, so it maybe drops some of those key speech frequencies that are highly related to intelligibility. So that SNR is going to be impactful. The other thing is that for a lot of these noise scenarios, especially the ones that are dynamic and includes lots of transients, not just babble, but also clinking and clanking of a cafeteria, a lot of the benefits of going to a much wider bandwidth transmission is going to be masked by the noise. The exception that we see is the car noise. And if you've ever driven in a car, you know that car noise tends to be very closely related to pink noise in the sense that it's very low frequency dominated and rolls off. So in some sense, the super wideband transmission there is able to, let's call it, escape the masking effect of the car noise, and it actually does win us a little bit. Now on the volume comparison side, we're just looking at the narrowband use case here. First of all, for hands-free mode, the RLR measured at the ear going from nominal to max is not actually that big. We're not winning much more than about 2 to 3 dB tops. And the other thing that we see is we most likely run into the physical and or electrical limitations of the device now that we are going for max volume for these noise scenarios. Again, the exception is going to be car noise, where we can see that max volume does actually improve the listening effort. I think part of the explanation for that is the fact that the noise suppressor in the human brain, for something as static as car noise or essentially pink noise, it's a little bit easier for the human brain to filter that out versus something like pub or cafeteria, where there's a high amount of transient and non-static activity. But again, this shows and emphasizes why we need to do this, because all of our expectations for, hey, let's improve the bandwidth, whether we do that directly through the call or we do that artificially through bandwidth extensions, those assumptions go completely out the window for the hands-free scenario, except for car, which of course begs the question of how sophisticated do you make your device? And then likewise for the volume comparison, we see a similar trend where bumping up the volume doesn't actually help, whether that is done by the user or the device itself is doing it. And as a designer, whether you're making headsets or whether you're making mobile phones, you can now use this information to start to plan and design your device for optimal listening effort performance, regardless of the background noise environment, regardless of where the user might be situated. That would lead to the best possible experience. So, to wrap things up, the key messages that we wanted to leave you with today was the fact that we now have this new approach for evaluating listening effort. It's akin to intelligibility. It sort of lives between intelligibility and quality. And that there's a new standardized MOS metric around it. The other thing is we briefly wanted to emphasize the fact that despite an abundance of metrics in this relative domain, most of them are not quite suitable for what we're trying to do here. And the listening effort application stretches across multiple types of products, multiple types of industries. We touched on ANC headphones today. We touched on mobile phones, and there's plenty more. And next session, we'll touch on the automotive application and the automotive use case. And I think the number one key point is the fact that we get results. The fact that we can even do this and get MOS scores are fantastic. And of course, when we end up dealing with MOS scores, we have the usual, it's fairly easy to comprehend that the MOS values go from a 1 to 5. We're dealing with binaural recordings. Listening to them ourselves is going to be a fairly easy way for us to correlate the scores that are coming out of the algorithm with the recordings that we've captured. It allows us to benchmark devices. It's just all around a really fantastic thing. Now, before I leave you for today, I just want to remind you that our microsite, optimizeaudioconferences.com, includes information where you can access white papers. These online seminar videos will be hosted there. And of course, I want to remind you that our next live session is going to be October 13th. We'll dive into listening effort, specifically as it applies to the automotive example. So with that, I would like to thank you very much for attending. It was my pleasure to be here with you today. Have a wonderful day, and I'm sure we'll be in touch soon. Thanks a lot.